All right, what I want to do today, our last day of class, is first just go through the homework that you turned in today. Make sure you're all okay with that, and talk about things you should know from chapter 11 for the final exam as we go through that. And also, there's a few other formulas you should know from chapter 11 for the final exam that I have not assigned homework problems about, but I might ask about them. I'm not positive. I think if I do end up putting problems about them on the final, I'll alert you. And you can put them on your sheet of paper for the formulas. Well, let's start by looking at the problems. And the first problem, was kind of a weird computation question, just to verify some summation properties. First two here. They seem kind of weird at first, especially the second one, but if you are careful, they work out. This one should make intuitive sense if you take the difference between all the data values in the mean and add up those differences, some of which will be positive and some of which will be negative. They should add up to 0. Quick verification of that. I won't bother putting the I goes from 1 to n here. That's assumed to be the case. Verification here is just to use a property of summations that you can essentially distribute the summation sign through. Like that. I does go from 1 to n here. And then use the fact that with the second summation, x bar is a constant. You're adding x bar to itself how many times? N times. So this is the same as n times x bar. Again, it's assumed I goes from 1 to n. So you're adding n x bars to itself. And then it's just a matter of using the formula for x bar. Excuse me. The formula for x bar is the sum of the xi's divided by n. The n's cancel. And you're left with this, which you can just right away say is 0. You also could write it as one summation, xi minus xi. You're adding up a bunch of zeros, or you can just say that is 0. The second fact is weirder. If you add up these products, and why are the x's lowercase and the y's uppercase? Well, it's because of the perspective of chapter 11. The perspective being what I mentioned on Tuesday a bit, that the x's are taken to be fixed numbers that you decide on ahead of time, and the y's are taken to be random variables. That's why the y's are capitalized. There's going to be a similar property that would be true even if the y's were numbers. With lower cases, they would still work. You don't have to think of those as random variables, but that's the perspective the book is trying to take. It's a matter of, well, foiling this out first, then using the fact that the summation distributes. By the way, when I say the summation distributes through parentheses like this, that's not really the distributive property that allows that to be true. It's really more of a, I guess you would say it's the commutative property of addition. Subtraction is really adding negatives, so you can always think of subtraction as being addition. And that's the way you'd want to think of it, is to use the commutative property. Use that, and then use properties like the fact that constants can be factored out of summations. And it should all work if you're careful. So first FOIL this out. First times first is this. Outside times outside is this. Inside times inside is this. And last times last is that. Then, what's that? Oh, yes, thanks. And then distribute the summation sign through, which again really is more of a commutative property. The summation sign is not a number, right? It's a symbol meaning sum. So I'm not literally distributing a number through here. Like that. And then I can write the summation of this thing. And let me go ahead and right away factor the y bar out in front because it's a constant with respect to the summation. I can do that, right? With constants, they can be factored out of summations, just like they can be factored out of integrals. And with the next one, the little x bar can be factored out. Started writing I goes from 1 to n there. And then with the last one, both the x bar and the y bar can be factored out. They're both constant. With respect to the summation, I goes from 1 to n, you really get n times x bar times y bar. Now go ahead and replace, like do the only thing you can do, replace the x bars and y bars with their formulas. That's the only thing that makes sense to try here. Capital Y bar is the sum of the yi's divided by n. Lowercase x bar is the sum of the xi's divided by n. Lowercase x bar, once again, is the sum of the xi's divided by n. Capital Y bar is the sum of the capital yi's divided by n. Simplify. In this one n will cancel. And what you're left with, ignoring that term, these three terms are all really the same. You're subtracting 2 of them and adding 1 of them. You can cancel. Yeah, cancel, say, this one with this one. And you're left with this. Where are we trying to get to? We're trying to ultimately say it's equal to that, where the, we got a yi and an x bar in there. Let's expand that and see if it works. Let's do the right-hand side. Summation little xi minus x bar times capital yi. Distribute the capital yi through like this. Then distribute the summation through. Factor out the x bar. And then use the fact that x bar is the sum of the x's divided by n. And that essentially does it, because once you do that, you see that this is the same as that. Just switching where we're dividing by n, but you know, you can put the divide by n in either spot. It's the same as multiplying by 1 over n, and multiplication is commutative. So it's a little tricky, but if you're careful in how you think about it, that's how to do it. Why bother doing it? Well, for one thing, it's just a little practice with algebra and summation properties and just making sure you understand. For those of you who are planning on taking applied stats in the spring, we will re-go through chapter 11 in detail, and I will want you to more carefully read pretty much everything. Will I test you on everything? That's hard to say exactly. I'm not making predictions ahead of time here, but I will want you to strive to understand everything. Mainly, so you see that there is a logic that can be gone through, a logical process that can be gone through to derive all the formulas in chapter 11 that are useful, including ones you should know for the exam, which we'll get to here. Let's go through the, well, I guess we should do, I want to do all the problems here. Let's look at number 12 next. 12 is a lot easier than it seems. In fact, when you know what to do with 12, I hope you realize what to do with 12. It's almost too easy. Like, did I really do it? 12 says, 12 is probably a more important problem to be able to understand, even for the exam, say, final exam. The estimator of the true mean of the dependent variable capital Y was given by this formula. Notice this is an estimator. This is a statistic. It's a random variable. How do you want to think of it? Thinking of these conceptually in the right way is key to getting everything, to really understanding the purpose of everything. conceptually, you want to pretend x is fixed. Okay? Given some little x, we're trying to predict, well, two things with the regression line. The mean of y given x, or an individual value of y given x. The same expression here as a statistic gives us the answer. In fact, the predictions for mu hat and y hat are the same. You use the same regression equation. Here, this expression is a statistic. Capital B0 and capital B1 are statistics. They are things that are computed from a random sample from the wider population. And different samples will give you different observed values, lowercase b0 and lowercase b1. This is all inferential statistics. But they have distributions that can be described, and that's part of the main point of the second section of chapter 11, is what are the distributions of these statistics, b0 and b1. Under the assumptions that we make, they end up being normal for one thing, with a certain mean and a certain variance. Surprise, surprise, normal. That's good. That's why we make the assumptions that we do. But here, they're as statistics, and ultimately, we combine them this way to get this statistic, which this would have a distribution as well. It's a random variable. B0, B1 are random variables. Mu hat's a random variable. X is not a random variable. X is a fixed number. But I could do different things for X and get different random variables here. As a random variable, I can try to find its expected value, its mean. Here's another situation where the mean of the mean is the mean. The expected value, theoretical mean of this statistic that is representing a mean, is the mean of y given x, which is a parameter, right? That's a theoretical expectation, expected value. This is a statistic. That's a parameter. There's no hat above it. It's a fixed but unknown number. The assumptions that we're making is that the parameter can be written as a linear combination, essentially, like that. Yeah, we're assuming this is true. It's the background assumption we're making, one of the background assumptions. But the mean of y given x, this unknown parameter, is a linear function of x for some unknown parameters, beta 0 and beta 1. It's an assumption. Is it really true? Probably not. This is applied math. Rarely are our assumptions exactly true. We just hope it's good enough. It's an assumption we make, hoping it's good enough that it gives us decent answers. That's what always happens when you're applying advanced math in real life context, engineering, business, whatever. You make the assumption so that you can get some sort of answer. And then the question is the answer reasonable or not? Can I use it to make money? Can I use it to help people? Can I use it to send spacecraft to Mars without them, flying off into the outer solar system? Which has happened, by the way. I don't know if you know. They've sent spacecrafts intending to have them go to Mars, but they flew past it because there was one situation where they just used the wrong units in their calculation, and bye-bye billion-dollar spacecraft. Okay. So assumptions are important, but you got to apply the assumptions correctly as well, and they need to be valid. Anyway, trying to show this, I gave you a hint. I said use properties of expected values. Like what? Well, also use the formula for mu hat. Capital B0 plus capital B1x. You must use capital letters, not lowercase there. These are statistics, random variables, not observed values. And then the expected value is linear. You can factor out the x, don't factor out the B1. Linearity of expected value. And then just use other facts that are derived in this section. Like, what's the expected value of capital B0 and what's the expected value of capital B1? They are in the reading, so you have to search for them. There's the distribution of capital B1, normal with this mean and this variance. Derived on the preceding couple pages with a lot of crazy calculations. Beautiful calculations. This is what you need to use. How? Just use the mean. It's beta 1. And guess what? The mean of B0 is beta 0. This becomes beta 0 plus x times beta 1. And that, based on earlier in chapter 11, is mu sub y given x without a hat. Done. That's all you had to do. Is using facts on pages 391, and for B0 it's page 392. The distribution of capital B0 and capital B1 as statistics, as they're normal with certain mean and certain variance, and the means are very simple. So it's easy, but you got to know what you're doing. You got to know the purpose of everything and what the meaning of these symbols is. What's a statistic? What's a parameter? That kind of stuff. And I know there's a lot of symbols and a lot of equations, so it all gets confusing. Trying to highlight the key things in chapter 11 without getting into the details too far, because it just take too long. So that's all you had to do, but you got to do the right thing. On to the problem with the spreadsheet, 16 and 17. I'm also going to look at 18, and 18 is the one that has us do something new today that we did not do on Tuesday, that I do want you to know for the test. Okay, so let's quickly do the same kinds of things that we did on Tuesday here with the spreadsheet. I think it's worth going through one more time here to review. So this is the problem about the jobs. X is the number of jobs, Y is the make span, which is the amount of time from starting the first job to finishing the last job. And they don't say what the units for Y are. It could be hours or something. Do the sums. 12 numbers. N is 12. Do the means, which I can do with either the sum numbers divided by 12 or equals average. Standard deviations equals STDV. Doesn't ask for the correlation, but for sake of just teaching you about it, we're doing correlation. Do you need to know the correlation for the test? Well, we never did correlation except in what I'm showing you right now. In that shortcut formula to find the slope, that is, once you've got the correlation in the standard deviations, is easier to use than the formula in the book. I guess I'm saying, I mean, you should be able to use the formula in the book, and you should know, and I guess be able to use this other formula for the slope if I give you the standard deviations and the correlation. I guess I'm saying you should know this. And the formula is, again, that the slope in terms of these three numbers is the correlation called R times the standard deviation of the Y's divided by the standard deviation of the X's. You don't find that in the book. That's something I'm teaching you. It's another way to calculate the correlation and is, or excuse me, the slope, and is certainly easier to use if you've got those three numbers. I didn't prove that. I'm just saying it works. I haven't even told you what the formula for R is, so we can't prove it. This is actually somewhat useful thing to know as well, besides just for computation's sake, because what it also says is that if you think about the meaning of slope as rate of change, along a regression line, the change in y is the slope times the change in x, and therefore, since the slope is this, you can also write that like this. And what that means is, oops, get rid of the B1. And what that means, for example, is if delta x, for example, is Sx, in other words, if I let x increase by 1 standard deviation along the regression line, then y along the regression line increases by r times the standard deviation of the y's. That's kind of an interesting thing and maybe useful. Why? Because if you replace delta x here with Sx, the standard deviation of the x's, the Sx is canceled. And I'm left with r times sy. That actually can be a useful thing to know sometimes. In standardized units, along a regression line, y always changes by less than x. Doesn't mean the slope is less than 1. If x increases by 1 standard deviation and r is less than 1, as it usually is, then y is going to increase by less than 1 of its standard deviations. R of its standard deviations in particular. Not going to test you on that, but it just wanted to mention it. But yeah, I guess I'm saying you should know this fact for the test in case I decide to ask you about it. Not in the book. So I'll use it here like this. Big enough to see. Try to make it bigger. It equals the correlation in B18 times SY in C17 divided by SX in B17. And then don't forget how to find the intercept as well. It's y bar minus B1 times x bar. I wrote that down last time. You should know that as well. Y bar, mean of the y's, minus B1 times x bar. And remember I said on Tuesday, the reason, well, okay, it's not the reason that's the formula. What this formula for B0 implies is that the point in the plane whose coordinates are x bar and y bar is always going to be on the regression line. It doesn't mean it's a data point, right? Because, you know, just because you take the mean of some numbers doesn't mean you get a data value. But it does mean the center of mass of the data points is on the regression line, and that's just, I mean, if you're trying to draw a regression line by hand, say, or something, that's a useful thing to know sometimes. So you should have gotten 1.16 for the slope and negative 1.44 for the intercept. As far as the graph goes, I hope you figured it out, or if you just did it by hand, it's fine as well. But insert a scatter plot, for example. Wanted to see a plot, choose a scatter. And you can customize it to include the trend line, which is the regression line, and r squared, which is the square of the correlation. I don't see the equation of the regression line in here. I know in Excel you can get the equation in there as well. Can you? I don't, let's see, do you remember how? It's not a drop down. That one there? Okay, there we go. Okay, yep. Negative 1.16 times x minus 1.44. This is not times r squared. That's just the value of r squared. That is the squared correlation. I'm going to cut that out. Although before I cut that out here, these data are a little strange. in that essentially we're going back and forth, up and down, below and above the regression line. That's not typical. That would, in real life, cause me to investigate what's going on there. Why is that happening? I mean, it's, you can see it in the numbers themselves. The make span for the next even number is the same as the make span closely, not exactly the same, for the previous odd number. Something weird going on there for these data. You'd want to, you know, investigate why if you didn't know why. What I'd like to, okay, let's get the analysis tool pack stuff as well in here. But then what I'd like to do is I want to, well, answer the questions 16 and 17 and also look at number 18 and emphasize formulas you should know, okay? So let's do the analysis tool pack here. Linear regression. Check the labels box. That's what I always do, at least. But include the labels in your Y range and X range if you do that. Output range is the upper left corner of the output. Let's make that be cell F18 maybe, or maybe, oh, F20. Residuals and residual plots I can make, but I didn't talk about them last time. So as far as now answering questions in the book, I mean, we already got the slope and the intercept. So we're trying to, in 16a, trying to estimate the linear regression equation. This is our population regression equation. We're assuming this is true. It's not the sample regression equation, but if I write down the sample regression equation, that would be my answer. That would be an estimate for the population regression equation. You could write it either with a y hat or a mu hat. It doesn't matter. And what you should have gotten is the same slope and intercept we already saw. And you can see it down here as well. So you should have written either y hat equals negative 1.44 plus 1.16x, or you could have written as mu hat equals negative 1.44 plus 1.16x. And it is in this regression output as well. And then you plot it. We saw the plot. 17, once you got this regression output, there's not much to do. 17 says, test for a significant linear regression at the 5% level of significance. If we've got this output, there's not much to do. You say, hey, there's the t-stat and the p-value. P-value is really small. Reject the null at the 5% level. It is significant, is what you would say, what you should have said. The test for significance means to test the null hypothesis that the regression slope, not the intercept, but the slope, beta 1, is 0 versus the two-sided alternative that it's not 0. That's what it means to test for a significant regression. And you say it is significant if you reject the null, if the p-value is really small, if the t-statistic is really extreme, which it definitely was here. T was very large, p was very small, definitely less than 5%. We reject the null at the 5% level. We say it is a significant regression. Question?
Yes. So what we, I know it doesn't matter, but what we have, but should we have the p-values? Or is it already the back one?
It is, this is already the two-tailed p-value. That's by default what this does, is the two-tailed one.
Oh.
It's probably related to the fact when people program this, that some people by default always do two-tailed tests, even if they have a theory that it should be right-tailed or left-tailed. Just again, to be conservative, make it harder to reject the null, make it harder to make a type 1 error. Doesn't really matter here because the p-value is so small. If we wanted a one-tailed p-value, since we double one-tailed p-values to get two-tailed p-values, if you wanted a one-tailed p-value here, you got to divide by 2. Divide by 2 instead of multiply. But it would be even smaller. So that's what you should have done for 17, is just look at that output. Could we do it without the output? Yeah, but you'd still need technology. If we were trying to do that test we just did without the output, or at least some other way, you might say, we'd want to use that formula right there to compute t. Then use n minus 2 degrees of freedom and either the table in the back of the book or the calculator. Well, n was 12, so n minus 2 is 10 here, 10 degrees of freedom. B1 was the slope. This formula is a statistic, all capital letters. Right, B1 is a statistic, it's got a distribution. S, this regression standard error, not a standard deviation, but it's called the regression standard error, is also a statistic. It's got a distribution. This, which I call SSXX, say it's also a statistic. Then we can convert these things, this formula, to lowercase letter when we take a random sample and actually observe values. B1 is the slope we observed. What was it? 1 point. Little b1 is the 1.1608, say. Go ahead and write this down. It is a formula you should be able to use if I ask you to, so you will want to put it on your piece of paper for the test. We're talking observed values here. Use lowercase letters. The B1 we got was the 1.1608. Regression standard error, S, as a statistic, as a capital S, its formula was square root of SSE divided by n minus 2. That's found by taking the square root of both sides of this formula here. SSE, we have always found so far with the spreadsheet, technically speaking, you could, well, you still need technology, but you wouldn't have, it's sum of squares of errors, which means sum of squares of residuals, because residual is synonymous with error. So we found the predicted, the y-hats, and we found the residuals and squared them and added them up. Technically, we could also use this formula right there, where this is SSYY, which we've never computed before. That's the first time I've shown you this formula. We've never used it. I'm not going to put this one on the test. Most likely on a test, I'd probably just give you SSE or something, just to help avoid mistakes, help make things quicker. But it's worth emphasizing one more time how you'd actually compute it. Emphasize one more time. Let's also compute SSXX and stuff. We'll need it anyway. On the spreadsheet, we'd take the x values and square them. This is to help us compute SSXX, sum of squares of x's, with that other formula that I showed you. It's 1226 here. The other formula I'm referring to here, that's not SSXX yet. The other formula that I'm referring to, well, here is the definition of SSXX. And I guess I'm using lowercase letters for the x's, but not a real big deal. But then I said that's equal to this. I didn't prove it. I've written that down a number of times. That's something you should know. So I've just found in the spreadsheet, I've just found that. That was the last column I computed the sum of. And I've already computed the sum of the x's in a previous column. So I got to do this expression now. N is 12. So SSXX, I'll put it down here. So the sum I just computed, that's the sum of the xi squareds, minus the sum of the x's quantity squared divided by n, which is 12. So SSXX here is 143. Coming back to this formula, that means I'm going to have a square root of 143 in there. I also want to compute S from SSE. So I need SSE. This column, I don't actually need to compute. I could compute it if I wanted to compute some other things, like, for example, the correlation in another way, but I don't really need it here. Let's do the y-hats. That's where you use the observed slope and intercept that are in cells B20 and B21 here. B21 is the intercept plus the slope in B20 times X. Dollar signs around the B's for the 21 and 20 because that's absolute cell references. Nothing around the B2 because that's a cell reference I want to change as I click and drag. These numbers should be close to the make spans that we actually observed, somewhat. Giving residuals that are somewhat close to 0. Compare these numbers with these numbers. Do a subtraction, y minus y hat for the residuals. You get a bunch of numbers that are relatively close to 0. About half of them are positive, about half are negative. The residuals actually have to sum to 0. Square them. And then add up those squares, and you get our friend SSE. It is about 7.61. That's the thing that's minimized. So you should know this concept. That's the thing that's minimized for our data. That's the minimization in least squares linear regression. It's designed to minimize SSE, which also means it's designed to minimize S, because that's the square root of SSE divided by n minus 2. Again, n is 12, so n minus 2 is 10. Regression standards error is about 0.8724. We can check it with the summary output. It matches this number right there. Standard error. .8724, 872,938, 0.872938. Calculation now for T. And 872,938 divided by square root of 143 is what the bottom simplifies to, about 0.073. Is that in the regression output anywhere? 0.073. Yeah, it's right there. The thing we divided by that I just calculated in the calculator, 0.073, is called the standard error of the slope. What does it represent? It represents an approximation to the standard deviation of the sampling distribution of capital B1. Capital B1 is a statistic. It's a random variable computed from a random sample. It's got a distribution. It takes on different values for different samples. What's the mean of that distribution? It's beta 1. What's its standard deviation? That's more complicated, but it can be approximated by what we divided by here. This thing. It was 5.073. Take 1.1608 divided by that, and we get our t-statistic about 15.9. And that matches that. And then the p-value from technology or table. It's an extreme t-stat, a small p-value, we reject the null. It's a significant regression, which means all this work to say, hey, now I feel good about using the regression line. I think I've got a good model. Or do I? Is this sample size large enough? It's only n equals 12. Maybe it's still not real great. Maybe I'd want a bigger sample size to get a better confidence interval, for example. I guess that's not too bad. It's close to, okay. I don't know. Anyway, what I'm trying to get across is we can confirm these things with the formulas when we've got technology to help. What does number 18 do? Didn't assign number 18, but I'm going to show you the formula you can use to do it, and you should be able to do it for the test. 18, parts A and B. When x equals two numbers, either x bar or 12, x bar is whatever x bar was. I think it was 9 something. Compute a 95% confidence interval for the mean. Not just a point estimate. Confidence interval. There's actually something else you can do called a prediction interval, which we will not take the time to do because this is enough. What formula is necessary there? I'll just tell you. This formula right here, page 399. Confidence interval on mu sub y given x, the mean value of y when capital X equals little x. It's mu hat, which you get from the regression line, right? Plus or minus, there's your margin of error. All that stuff we know how to compute now. For our problem, n is 12. SXX is what I call SSXX. Computed that. S, that's the regression standard error. We computed that. X bar is whatever the mean of the x's is. X there, what's the x there? Well, whatever you decide you want it to be. And the problem, they say first let x equal x bar, which, hey, that would make this fraction 0. And then in part B, they say let x be something else. What about t alpha over 2? Well, that's a t statistic, a critical value from the table or your technology based on a certain level of confidence related to alpha and a certain degrees of freedom. How many degrees of freedom? N minus 2. It's always n minus 2 here in chapter 11. In applied stats, we'll get to chapter 12, and then degrees of freedom sometimes is n minus 3 or even n minus 4 or n minus 5. It depends on the number of explanatory variables. Simple linear regression only has one explanatory variable, x. So many formulas, so many symbols. But there is a unity to it all, a consistency that we do the same kinds of patterns that we do over and over again. It's just that situations change and formulas change. But they are similar to each other in various respects. Let's go ahead and compute that here. Let's do it for part B. When x is 12, this is 18b, x is 12. Let's write down the numbers we need. We need the X bar. That's 9.5. Just the plain mean of X's. X bar is 9.5. N is 12. We need the SSXX. That was 143. We need S. That was 0.872938. I got those from looking up here. Say we want 95% confidence, which is what we want, then alpha is 0.05. So alpha over 2 is 0.025. How many degrees of freedom there are there? DF or gamma, if you prefer, is n minus 2. That's 10. So T sub 0.025, I'll just look in the table. Our critical value. 10 degrees of freedom. I need to look for 0.975. 10 degrees of freedom, 2.228. Is T. What else do I need? I need the mu hat. I need to use the regression line, the slope and intercept. Plug in x equals 12 into the regression line. You could say mu hat of y given 12, if you like. To emphasize x is 12, maybe I should write an x is 12 there. Negative 1.4418 plus 1.1608 times 12. About 12.49, say. Does that make sense looking at the data? Yeah, seems reasonable with the data. So the answer is going to be, looking at the formula on page, what was it, 399 or something? 399. Formula being this thing again here, mu hat plus or minus T alpha over 2 times S times square root of 1 over n plus x minus x bar squared over SSXX. So that's going to be 12.49 plus or minus 2.228 times S is 0.872938 times square root of 1 over 12 plus 12 minus 9.5 squared over 143. Yeah. Let's do it. I go from right to left here. 12.9, 12 minus 9.5 is 2.5 squared. Divide by 143. Add 1/12 to that. Take the square root. You can do this fairly fast. Times 2.228 times 0.872938 gives about 0.69. So we get about 12.49 plus or minus 0.69, and you could write that in interval notation as well, if I have not made a mistake. So you'd say you're 95% confident that the mean make span when x is 12 jobs is in this interval. If we wanted to predict the next make span when x is 12, that's where you use the other formula, which you will not have to use for the test. Page 401, called a prediction interval. And the only difference between this formula and the previous one is the 1 plus in there, adding 1 under the square root. That's the only difference. But it actually can make this margin of error a lot bigger, just adding 1 to this, because the part without the 1 typically is pretty close to 0. And its square root is typically pretty close to 0. And so if you add a 1 in there, even though it only makes the square root about 1 unit bigger, as a multiplier, it could be 10, 20, 30 times bigger. Your margin of error could be a lot bigger for prediction interval for estimating the next y value, the next make span, when x is 12 jobs in this context. You don't have to know this one for the example. I won't test you on that. Take a 30-second stretch. That took most of class. So, I mean, this is all right if I haven't made a mistake. I mean, I could have made a mistake here, but. For our remaining time, which is only 15 minutes, we need to review everything else. Ha ha ha. Probably what's better in 15 minutes is just to take a step back and think about what we've done big picture wise instead of going into details. And we can do that by paging through the book and thinking about it and maybe even appreciating what we've done. Where did we start? We started with basic probability. Look at that simple formula, right? Formula for the probability of an event when you got equally likely outcomes. So thinking about sample spaces is always the beginning of probability. But then when you think about sample spaces, the problems can get pretty complicated pretty quickly when you do have to think about combinations and permutations, which are all derived from a fundamental principle called the multiplication principle, which really is just the meaning of what it means to multiply whole numbers. Looks fancy. An experiment taking place in k stages where n sub I is the number of ways each stage can occur. I goes from 1 to k. You multiply all the n's to figure out the total number of ways the experiment can occur. Sounds really fancy, but really is just describing what whole number multiplication means. I can have 4, what's the word? Appetizers, 6 main dishes and 3 desserts. How many choices for meals are there? 4 times 6 times 3, and you can make a tree diagram to show them all. And that principle, simple as it is, leads to the derivations of the formulas for combinations and permutations. And the key thing is with permutations, ordering matters, and with combinations, order doesn't matter. So you want to make sure you practice some of the problems about combinations and permutations that were found, maybe only one of them on exam 1. I don't remember if I gave you 1 or 2 problems on that. And I mean, yeah, you should be able to use the formulas instead of just plugging them in your calculator. You should know these formulas and be able to use them if I ask you to show your work. And again, I'm not changing numbers, changing functions, changing wording, changing answers. And I could change the wording enough that maybe I'd have you show your factorials. Whereas maybe on an old exam, I did not have you show your factorials. So you should be prepared for that if I asked you. Okay. I'm not ruling that out. Chapter 2 moved on to probability laws, including theorems that we needed to be proved. We have a proof on exam 1. I don't remember. Maybe I might have had a proof on exam 1. The proof on the final. I don't know. I'm not completely ruling it out. I might say I'm unlikely to, but still we're studying probably. The exact same one. Maybe something related. Maybe. So you should think about, and there was a homework assignment where you did some of these, so you should look at them at least and think about them. There's the general addition rule that works no matter what. This always works. It's always true. In the case where A1 and A2 are mutually exclusive, disjoint, it simplifies to this, which was really an axiom. instead of a theorem to prove. And it also got extended to more than 2 events. Conditional probability, by definition, is this formula. This is not a theorem to prove, that's a definition. What does conditional probability mean? It means this: probability of A2 given A1. The given one is always the second one, and you always divide by the probability of the second one, the given one. Multiplication rule in general, the general multiplication rule involves conditional probabilities. That's this one, this is the general multiplication rule. This is always true. Special multiplication rule, this first one simplified to the probability of A2 when A1 and A2 are independent. Independent events, the book calls this a definition, but I call it more of a theorem. And calls this a theorem, but I call it a definition. This one makes more sense as a definition because it's really, in a sense, explaining what independence means. The conditional probability of A2 given A1, what's the chances of A2 occurring if you know A1 has occurred? If they're independent, it shouldn't matter. Knowing A1 has occurred shouldn't matter. It should be the same as the ordinary probability of A2. And same kind of thing with this one. This is better thought of as a definition. And then this becomes a theorem, the special multiplication rule. Our book takes this different approach, which is technically okay, but to me it makes, and to Dr. Wetzel, it makes more sense to go the other way around. And we use this rule, we use this independence rule all the time in this class, really. Not only in chapter 2, but in chapter 3, when, for example, deriving the formulas for the PDFs of geometric and binomial random variables, for example. Comes up in chapter 5 when we think about joint PDFs. And technically speaking, it comes up in the statistics chapters when we derive, we assume independence to be able to use this to derive some other formulas. Or to derive, in particular to derive a formula for variance, which we'll come to here in a second. Bayes' theorem is in here. Disease testing problem is a typical kind of problem I tested and was on exam 1, could be on the final. Bayes' theorem. You don't need to know this real general thing. It was helpful to make tree diagrams. Help me just do the calculations in kind of an intuitive way. Chapters 3 and 4 get into distributions. Discrete in chapter 3, continuous in chapter 4. So we got PDFs and CDFs, or again, technically more correct in chapter 3 to call them PMFs, probability mass functions, but our book uses PDF. With discrete distributions, discrete random variables, you find the probability that X equals something specific, some specific number, by plugging into the discrete PDF. And getting a value, you don't have to integrate. In chapter 4, with continuous, the probability that X takes on any particular value is 0. Because the integral is the way you compute probabilities. Integrating from A to A, if A is a constant number, it gives you 0. There's no area under the curve. Your probability of observing any particular exact value in a continuous model is 0, which seems weird because we do observe values, right? We got a variable that's continuous and we can make a measurement and observe a value. Well, in reality, with continuous variables, when you say you observe a value, you're really rounding. So you're really observing a range of values. That's the reality of what happens. We don't really talk about that, but that's the reality of what's really happening when you observe a value of a continuous random variable. Like you say the answer is 3.47. Well, you really mean it's somewhere between 3.465 and 3.475. Standard kinds of things to do are to find the expected values, E of X, or in general, E of h of x, and the common things to use for h of x are x squared, x squared, x minus mu quantity squared is the definition of the variance. We also did e to the tx when we do moment generating functions, where t initially is thought of as fixed, but then in the end it becomes a variable. Yeah, that's the definition of the variance, but here's the shortcut formula that we always use. Rules for expected values, these work no matter what. The corresponding rules for variance, the first two work no matter what, but although the second one gets modified, well, the first two actually do get modified for variance, but the third one for variance only works when you assume independence. That's a key place where independence is important. This is only true when x and y are independent. And that was important for later derivations in statistics. For example, distribution of x1 bar minus x2 bar, assuming x1 bar and x2 bar are independent when we're doing random samples from two populations independently. Moment generating functions, special random variables, geometric, binomial, Poisson, those were the main discrete ones. Continuous, special ones were gamma, and the subdistributions were more important, exponential and chi-square. Also, normal, big one. Uniform, sometimes you encounter uniform. Our little subunit about actuarial math, actuarial science math. From those handouts. Chapter 5 was joint random variables, bivariate with 2. You can generalize this stuff to 3 or 4 or whatever. Independence is important. To say this is true if and only if x and y are independent. The joint density is the product of the marginal densities. If you just write down an arbitrary joint density and calculate the marginal densities using an integral, say, in the continuous case, in all likelihood, it will not satisfy this. But when we do some theory, for example, the statistical theory with random sampling, technically speaking, in the background, we are assuming the variables x1 through xn in a random sample are independent, and therefore this kind of equation would be assumed to be true. But we didn't really need it much. Covariance is this, and there's a shortcut formula for that. That was this. And it was true that if x and y are independent, then the covariance is 0. But it's not true to say that the covariance being 0 means x and y must be independent. Unfortunately, that's not true. And this example with this table verifies that. A situation where the covariance ends up being 0, but the variables are not independent. Other stuff we did here included, marginal densities, conditional densities, curve of regression. These did come up on old exams. Running really low on time here. After this point, we got into statistics with kind of a theoretical interlude in chapter 7 with stuff like theory of estimators, unbiased, method of moments, maximum likelihood, fingerprint theorem, to come up with distributions for sums of independent random variables. And then after that point, we really got into the statistical test, the confidence intervals, and the hypothesis testing. And then ultimately here, regression is a statistical model. Main 3 things you do in theoretical statistics: confidence intervals, hypothesis testing, and model building. And there's all sorts of questions that we haven't talked about that you could think about in your statistics. Like, for example, t-tests, technically speaking, are based on theorems where you assume your population is normal. Well, what if your population is not normal? Do our t-tests, do our confidence intervals still give us reasonable answers, or do we have to modify them? Those are examples of kinds of things that you do in more advanced stats classes, like in grad school or something. Okay, and there are, unlike math, more so in statistics, there are people who have different opinions about best methods because it's not always so clear. A lot of content, as usual in math classes. It's unavoidable, especially when you have to put these things into one semester. But I hope you feel like you learned a lot. Mm-hmm.
So I know you said it'll be a similar length, but probably a little bit longer.
A little longer, yeah.
So do you have an idea of?
Well, instead of an hour and 50.
Sections or chapters that you focus on more recent stuff, or is it more of a?
I don't know for sure. I'm imagining like approximately 2 questions from each of the 3 exams, approximately, though if it's true false, maybe there'd be more from one. And maybe 2 or 3 or 4 questions, depending on their length, of newer stuff from chapters 9 through 11. Okay. All right.